So in Standard 14, we're going to look at polynomial functions and try to have the ability to graph them with some very specific points of accuracy, meaning that we're not necessarily going to graph them as accurately or as precisely as we did some of our toolkit functions earlier. But there are some specific things that we want to look for in terms of determining if our graphs are accurate here. So we'll talk about what that means as we go through this section. But first of all, when I say a polynomial function, what am I talking about? Well, in the last standard, when you studied quadratics, that was a polynomial function. It was a very specific one. What we're going to look at is kind of more general polynomial functions. And, here's the definition of it, okay? Where, let me give an actual example here, make it a little less abstract and say, okay, so there's my polynomial. Okay, so what makes it a polynomial? Basically, that what you have are x raised to whole number powers. Okay, x is raised to whole number powers. So if I had x to the 1/2, that would not work for a polynomial, right? They've got to be whole numbers in the exponents for your variable terms. Okay. And even though you can see here you've got x to the n, then x to the n minus 1, it's totally fine for you to just skip over certain powers. Okay, so like this one doesn't have an x cubed power, and that's totally fine. All right, so that's what we're talking about when we're talking about polynomials. Now here's the two things that we want to be able to do with polynomials, the two ways in which we want to be accurate when we're graphing them. And that is in the long run behavior and in the short run behavior. Okay, and I'll introduce those one at a time. So long run behavior just simply means like what's happening on the large scale, right? If I was to zoom out, what is the graph basically doing when the x's get really negative or the x's get really big? Short run behavior is what is happening near zeros, okay? So we'll go through each of those, but we're going to start with long run behavior. All right, and to introduce this idea of long run behavior, what I've done is I've put all these different, this should be an equal sign there, I don't know why it looks like that. But we have all these different graphs here. First of all, if x equals x, then x squared, then x cubed, x to the 4th, x to the 5th, x to the 6th. Now we should start to see a pattern here. Notice that every time the power is odd, when x is negative, the y is negative, and when x is positive, the y is positive. Whereas with the evens, the y values are positive and get really big no matter what the x values are, positive or negative. So what you can actually generalize as you see this pattern here is if we say y equals x to an odd number, then basically it looks like this. Okay? And if we say y equals x to an even number, then basically it looks like this in the long run. Okay, and so that's what we're talking about long run behavior. If I let the x's get big, where are the y's going? If I let the x's get really negative, where are the y's going? All right, so we can use that principle here, and we'll do that on the next page. It says to determine in behavior or long run behavior. If I slip up and say in behavior, it's the same thing. Our textbook uses the phrase long run. I'm just in the habit of saying in, so if I accidentally mix those up, they're the same thing. All right, so what we need to do is think about what happens as x goes to infinity and x goes to negative infinity, right? X gets really big or x gets really negative. All right, so when it says determine the long run behavior of y equals x to the 8th, okay, I know that based on what we just talked about, since it's x to an even number, I know that it basically looks like this. And so because I know it looks like this, here's the way I would state the long-run behavior. As x goes to negative infinity, so when I use that arrow, it means goes to, f of x goes to, well, as x goes to negative infinity, f of x, or the y's, go to positive infinity. And as x goes to infinity, f of x goes to infinity. So this is what I mean when I'm talking about the long-run behavior, okay? And so in this one, we talk about g of x equals x to the 11th power. Well, based on what we talked about on the previous page, if it's odd, the basic look is this. So this one, as x goes to negative infinity, so does the function. G of x also goes to negative infinity, as we can see here, negative, negative. And as x goes to infinity, g of x goes to infinity. All right, so that's what I'm asking for long-run behavior. Okay. Now, let's think about here what happens when things get a little bit more complicated. Okay. So if things get a little bit more complicated in this sense, before I jump into example 3, let me give a simpler problem. Y equals x to the 4th power plus 2x. Okay, so like let's say I have that. What we can state is that the long-run behavior is the same as y equals just x to the 4th without this extra 2x. Okay, why is that? Well, remember with long-run behavior, what you're doing is you're plugging in either big x values or really negative x values. So like negative 100 versus 100 or 100. So if we think of plugging the number 100 in here, if you take 100, let's just do that, y equals 100 to the 4th plus 2 times 100. So that's going to be 200, right? But if you take 100 to the 4th power, you know what you're getting? You're getting that. So you've got 100 million. So let me just ask you this in terms of money. If you won $100 million and then you lost your wallet that had $200 in it, are you really going to care very much? The answer is no, right? Compared to 100 million, this 200 number is insignificant. So what that tells us is that when you are trying to determine the long-run behavior of this big, long polynomial, you can just focus in on the leading term, okay? The highest degree term. And whatever the long-run behavior of that is, that'll be the long-run behavior of the entire thing. Okay, so what if I take something like this? It's all factored and everything. How do I determine the long-run behavior? Well, you don't have to multiply it all out, okay? What we're going to do as a strategy here, let me change colors since I've written a bunch in green here. As a strategy here, we're going to figure out the leading term. That's all I really need to do. Figure out the leading term. We don't care about the rest of it in terms of long-run behavior. Let's just figure out the leading term. Okay, so as we do this, let's think negative 4x, 2 plus x, and then x minus 1 cubed. Okay, so let's start with this x minus 1 cubed. We know that if we multiply x minus 1 times x minus 1 times x minus 1, it's going to be pretty big, right? But I think we can agree that all that really matters is that x cubed is going to be the highest degree term that comes out of this, right? Okay, and a whole bunch of other stuff's going on over here, but you're going to have x times x times x. All right, so we've got that. Okay, now when you multiply this by 2 and this by x, you're going to get lots and lots more terms, right? So again, let's not overly burden ourselves here with too much detail. I think we can agree that the very highest degree term you're going to get is this x cubed times this x. So you're going to have x to the 4th, and then you're going to have a whole bunch of other stuff, right? But who cares what it is? And then lastly, negative 4x times x to the 4th is going to give you the very highest degree term. So you get negative 4x to the 5th plus a bunch of other stuff. Okay, so that is what h of x looks like. Okay, so now our task is simply to figure out what is the long run behavior of that. Well, it's an odd, right? So when there's an odd power, right, you're going to have negative on one side and positive on the other. But there's also this negative out front. And what does a negative do? It vertically flips the graph. So what we have here is that this one's going to have this sort of behavior to it. Okay? And again, just going back to the previous page real quick, we decided that x to the odd looks like this, but what happens if you vertically flip it? Well, then this goes up here and that goes down there. And that's exactly what we just did because we saw the negative out front. And so, to write it out in phrases as we did in those couple examples at the top of the page, what we can say is as x goes to negative infinity, h of x goes to positive infinity. Oops. And as x goes to positive infinity, right, when it goes positive, the function values or the y values go to negative infinity. So that would be the way I'd actually write that out. All right, so that's long run behavior that we're looking at there. All right, so now let's talk about short run behavior. What are we talking about with short run behavior? So as we said on that first page, short run behavior is all about the zeros. So this brings us to this series of statements that are real about real zeros of polynomials. Okay, let me just read through them and then we'll see how that applies. So if you have a number that is a zero of the polynomial, that's the same as saying that x equals c is a solution to the polynomial being equal to 0. Okay, well, yeah, that's what it means to find a 0, right? It also means that x minus c is a factor of the polynomial. And then finally that c0 is an x-intercept of the graph of the polynomial. All right, so let me just kind of clarify what all this is saying, particularly number 3 here. Okay, so if I gave you f of x is equal to x squared minus 5x plus 6, okay? If I'm trying to find the zeros of this polynomial, number 2 says that's the same as setting the polynomial equal to 0 and solving, right? That's what number 2 is saying. And you could solve this one pretty easily by factoring, okay? X equals 2, x equals 3 are your solutions, okay? So you can see it right here. 2 and 3 are zeros. So what does that mean? That means that x equals 2 and x equals 3 are solutions to that equation. It also means that x minus c, so in this case x minus 2 and x minus 3 are factors of the polynomial. So in other words, if I would have started with the polynomial looking like this, then that would have been the same as what I wrote out here, right? So they're factors of the polynomial. And then of course we know this fourth one, when you find those zeros, you're really finding the x-intercepts. Okay, so that's kind of to put an example to what all these different statements are actually saying. Okay, so so I could, if I wanted to kind of number this, I'd say 1 is saying that. 2 is saying that, 3 is saying that, and then 4 is just what flows naturally from these. All right, so that's, first of all the things we want to think about when we're thinking of zeros, okay? And so just to jump down to example 4 here, what's the point of me saying all these equivalent statements? Well, the point is I can just look at this because it's already in factored form, and I can tell you that x equals 0 is a 0, x equals 4 is a 0, and x equals -3 is a 0. Okay, so that's why we kind of introduce all these, so that we understand that relationship between factored form and what the zeros are. All right, but there's one more piece to this puzzle that we need before we can put it all together and be able to actually graph something like an example 4, and that's this idea of multiplicity. Okay, so it says that if x equals c is a 0, so a particular number is a 0, and the factor x minus c occurs exactly m times in the factorization, then we say that c has a multiplicity of m. Okay, and the whole reason we care about that is because a graph with a 0 of multiplicity m will behave like y equals x to the m near that 0. Okay, best way to make sense of this is just to dive right in. Okay, so let's first of all list out the multiplicities of these zeros. So x equals 0 has multiplicity 2, right? Because there is the second power on the factor that produces 0. X minus 4 is multiplicity 1, and x plus or x equals -3 is multiplicity 1, because for both of those factors there's just really a 1 up there. Okay, so what that means is that near x equals 0, let me just write it out that way, x equals 0, the graph looks like y equals x squared. And then near x equals 4 and -3, the graph looks like y equals x. Okay, so what does this mean, looks like? Well, let's think about what y equals x squared looks like. It looks like this, right? And y equals x, what does it look like? It looks like this. Okay, so at this particular 0, what we're going to do is we're going to go down and touch the 0 and then rebound up off of it, just like a y equals x squared does. But for these two zeros, we're going to cut straight through the x-axis, just like y equals x does. Okay, so that tells us that we've got these zeros here. Let me actually use some tick marks. So we've got these zeros here, and now we know what they should behave like. So the only other thing we need to do to get an accurate graph is to talk about the long run behavior. So the long run behavior, let's erase some of this extra stuff here. The long run behavior of this function, remember what we just learned, is determined by the highest degree term. So the highest degree term, well, when you take this one times this one, that's going to give you x squared. And when you multiply it by x squared, you're going to get x to the 4th. So g of x looks like x to the 4th plus other stuff. I'm not going to bother to figure out what it is, but this is the highest degree term. So what does y equals x to the 4th look like? Well, we know that y equals x to the 4th looks like this. So this tells me that in the long run, as x gets really negative, y is going to go up toward infinity. So I'm going to put a little arrow up here to match up with this arrow that's down here. And then when x gets really positive, so does y, and so I'm going to put a little arrow up here to match up with that. And so what that does is it gives me the place to kind of get started, okay? So because I know I end up just shooting up to infinity here in the end, in the long run, now what I can do is I can kind of start at that arrow, and now I can come down and approach my 0. So I'm going to have to go through this 0 right here of -3. And what I learned over here is that I should cut straight through, just like y equals x cuts straight through. So I'm just going to go through and go like that. Now eventually I got to get back up there to this 0, right? So I'm going to go up there. Okay, but what did we decide? We decided that because our graph is behaving like y equals x squared, instead of cutting through my 0, I'm going to rebound off of it like that. But then I'm going to have to come back up because I got to get myself to my last 0. And I cut straight through, right, because of its multiplicity. And I connect up with my arrow up there. All right, so you can see how this all comes into play. Figure out your long run behavior, put your arrows in the right spot. Then starting from there, you've got to make it to all your zeros. But when you're at each 0, you've got to obey what the multiplicity is telling you to do. All right, don't worry, we're going to do a lot of other examples of this. This is one of those, they're kind of fun problems actually, but they do take a little getting used to. All right, so let's try example number 5 here. All right, so this time we're going to start with the long run behavior. That's usually the best place to start, even though I kind of did it in the reverse order last time. Long run behavior, okay? So let's think about if you were to multiply all this out, what would be the largest term that would come out? The largest would be x cubed. There'd be other stuff as well. Okay, so y equals x cubed is the long run behavior. So that means, well, we know that y equals x cubed graphs do this, right? So what that tells me is that I can definitely put an arrow down in the negative down here to match up with this arrow here. And then over here I can put a arrow up here in the positive. Okay, and that's just to kind of remind me generally what's going to happen. Now I go to my zeros. So my zeros are x equals -2, x equals 2, and x equals 3. And all of these have multiplicity 1. So that means they're all just going to cut straight through just like y equals x does. All right, so we'll mark these. So we'll go 1, 2, 1, 2, 3. And don't worry if you don't connect up with these arrows perfectly. They're just there to kind of help you. So like this one, I kind of want to move over a little bit, which is fine. And so we're going to do this. I know I need to cut through this 0, and this 0. So I'm going to go up here. All right. And then I need to get myself down again so that I can hit this 0. And again, it's going to cut straight through, but then I'm going to have to pretty quickly turn back around so that I can still cut through this 0. So do you see what I mean by, hey, I didn't hit that exactly, but it helped me to know where I needed to end up in the end. Okay. Now, let's just take a break here for a second before we move on to the next one, and let's make sure we're understanding this idea of long run behavior versus short run behavior, short-term behavior. Okay, so I'm going to go to the calculator here for a moment. All right, go to my y equals menu, and I'm just going to type in exactly what we were just working with. X plus 2, x minus 2, and x minus 3. All right, so I'm going to graph that just on the standard window, and that's what you get. I don't think I did a terrible job of making a sketch, right? Going back here just real quick, right? I think I did a pretty decent job of that. All right, but what are we talking about when we talk about long run and short run behavior, right? Because this doesn't look exactly like y equals x cubed, even though we said that was the long run behavior. The idea here is if I zoom out, the more I zoom out, the less detail I'm going to be able to see in here. And you notice here, when I've zoomed out a whole bunch, you really can't tell the difference between what I have and y equals x cubed, right? It looks like it's just y equals x cubed in the grand scheme of things. So that short run behavior, yeah, it's important, but when we talk about long run behavior, we're just talking about like, hey, if I zoomed out enough, I really wouldn't be able to tell the difference between this and y equals x cubed anyway. All right, let's do another one here. And what I would say is at this point you might still be trying to get comfortable with all this. So feel free to just kind of let the tape roll here, and you know, if you're not feeling quite ready to do it yourself, there's a couple more examples coming up on the next page of your notes, and that would be a great time for you to just go ahead and try some on your own before you watch my solution. All right, so let's go with this here. Let's talk about long run behavior. So in the long run, what's happening? Well, the very highest place value, right? There's an x in here. Very highest place value here is an x squared. So it would be x times x squared times x cubed, right? And we add up all those exponents, that gives us x to the 6th. So this will be 1/20th x to the 6th plus a bunch of other stuff, right? So this is the behavior of this graph in the long run, which is, well, since it's x to an even, it's this. All right? Okay, so I know then I'm starting up here and I'm ending over here, right? Both arrows have to end up going up to infinity on the edges. All right, so what are our zeros? Well, we have x equals 0 coming from this factor. And it has a multiplicity of 3. Okay, so this is the first time we've seen multiplicity 3. It means exactly what you probably think it means, right? Y equals x cubed, okay, is what the graph behaves like near here. So graph behaves like y equals x cubed near this 0. Okay. All right, then we have x equals -6 with a multiplicity 2, which we've already discovered, right? Behaves like, behaves like y equals x squared. And then x equals 5, right? That's multiplicity 1 because that factor is only raised to the first power. Okay, so let's go ahead and chart this out. So we've got 1, 2, 3, 4, 5, 6. And then we've got 1, 2, 3, 4, 5. All right, so we've got to hit here, we've got to hit here, and we've got to hit here. Okay, so you can see my arrow's probably off a little bit. So I'm going to kind of maybe go more over here. So -6 is multiplicity 2, right? So as I come down here, I am not just going to cut through, I have to rebound back up because of the fact that it's multiplicity 2, right? It needs to look like y equals x squared there. Then I've got to get myself back down again to be able to cut through here. Okay, now, what does y equals x cubed behave like? Remember that y equals x cubed doesn't just cut through 0, it kind of does this little kind of cubic, we call it kind of like a cubic jog, right? So it kind of hugs the x-axis here pretty closely. So I'm not just going to cut straight through, but I am going to switch from being positive to negative, just like y equals x cubed changes its sign as it goes through at 0. But what I'm going to do is I'm going to kind of do this. I'm going to do that kind of cubic action as I go through there. And then I'm going to dip down. And then I'm going to come back up so that I can meet up with my long run behavior on the other side. All right, now, while you need to be able to do this completely manually, as I'm doing it, there's nothing wrong with checking your work. I think, especially because this is kind of new to us, we definitely should do that. So let's just punch it in our calculator and see if what our calculator is showing us is the same thing that we got. So 1/20 x cubed, and then we have x plus 6. Oops. Oh, I hate it when I do that. If you have a calculator like mine, you got to be careful with that, where you think you're just typing away at the equation, and then it's all still up in the exponent. It's kind of annoying. All right, and then that's raised to the second power, and then we have x minus 5. I'll go to zoom standard. Okay, so looks pretty reasonable, I think. Oh, I meant to hit zoom standard. I don't think I did though. Let's try that. Ah, that's better. Okay, so general shape looks good. You know, you might change your y values a bit to get a better picture of this. So, you know, maybe go like negative 100 to 100. X values are fine. Okay, you can see a little better. But overall, I'm pretty satisfied. I can see that there's definitely that behavior like y equals x squared here, the behavior like y equals x cubed here, and then cutting straight through like y equals x in that last 0. All right, now these two, I would really like you to pause the video and try on your own, and then go ahead and push play again, and you can see how these two should have come out. All right, so in this first one, for the global behavior, or the long run behavior, excuse me, I'm using my old language again. The long run behavior. What's going to come out of here? Well, you're going to get an x squared out of this one, an x squared out of this one, and an x out of this one. So y equals 3/20 x to the 5th is what that ends up being when you multiply out. So x to the 5th is odd, so you know it's down here and up here. Okay, we know that in the long run that's what's got to happen. But in the meantime, right, we have a 0 of x equals negative 4. It has multiplicity 2, right? X equals 6 with multiplicity 2. And then x equals 2 with multiplicity 1. Okay. So let's go ahead and mark these. So we got negative 4, a 0 there, a 0 at 6, and a 0 at 2. All right, so this long run behavior, so this negative 4 is multiplicity 2, so I'm going to come up. I'm not going to cut through it because I got to rebound off of it like in y equals x squared graph would. But then at some point I got to make a turn, right? Because I got to get back up here to x equals 2, and that one has multiplicity 1, so I am going to cut straight through there, right? But then I'm going to have to get myself back down again at some point. Oops. Get myself back down here. And this is multiplicity 2, so I got to rebound off of it and then go up to match up with what I had here. And I missed my arrow, but who cares, right? That was just kind of a placeholder to make sure I was going to the right spot. Notice one thing, I didn't mention this in the last one, I'm not even labeling my y-axis here really. I understand that maybe it's a little inaccurate when I go to check it in the calculator, but you don't even need to label it, right? Where do I want you to be accurate? On the long run behavior, and then this behavior near the zeros. Those are the places we need accuracy. All right, so for this one, long run behavior. So we get an x squared here, we get an x here, an x cubed there, but with a negative 3 over 100 in the front. So this thing is going to be negative 3 over 100, x to the 6th. Okay, so since there's a negative there, we know that it's basically doing this in the long run, right? Y equals x to the 6th, but flipped over the x-axis. Okay, so both arrows are pointing down. And then we have our x equals 0 with multiplicity 3, x equals 8, multiplicity 1, and x equals negative 5 with multiplicity 2. So let's see, here's 0, and then we got to go 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5. Okay. So let's see here. We're going to start down here. X equals negative 5, multiplicity 2. So as I approach that thing, I know I've got to rebound off of it, just like that. And then I've got to come back up toward x equals 0, but I'm going to cut through it like a cubic would, right? So I'm going to do that. And then I'm going to go up here. And x equals 8 is multiplicity 1. So as I go through there, I'm just cutting straight through for that part. All right, so hopefully you got something that looks kind of like that. All right, so been a long video, I know. Just a couple more types of questions I want you to take a look at here. So as I look at this, hopefully now, as you look at it, you recognize some important features like these zeros, right? So like for example, I have x equals negative 3 is a 0, I have x equals 1, and I have x equals 4, right? Those are all zeros. And furthermore, I know how that should translate into factors. Okay, so if I wanted to write a function for this thing, I would have, well, for this one, x plus 3. And because it rebounds back up, that must have a square on it, right? So that it's multiplicity 2. Right? And x equals 1 has multiplicity 1. So what factor produces a 0 of x equals 1? X minus 1. And it's to the first power. And since x equals 4 has multiplicity 3, this is going to be x minus 4 to the third. Okay? That right there produces a graph that basically looks like this. And in fact, if I go to my calculator and I punch that in, we can probably be relatively satisfied with what we see. And as you look at this, I encourage you to think about whether what we're seeing is the exact right answer or maybe just something close to it. Okay, so we're going to go ahead and make graph now. All right, so if you look at that, that looks kind of like what we see on the page, right? Let me go back to standard here, actually. Okay, looks kind of like what we see on the page, but looks like our, oh, I must not have hit standard again. There we go. But at the same time, things are looking, different just because it looks like we go up to really high y values here and really low y values down here. But if we look at our graph, notice that our graph doesn't go up too high and it doesn't go down too low. And in fact, it has a y-intercept that's really noticeable, a y-intercept of y equals 4. And 1, 2, 3, 4. This one's not going through y equals 4. So there is still something wrong here. Okay, it's definitely still something wrong. All right, so let's think about what that could be. Well, what I'd suggest is let's go back a page. Notice how this one had this negative 3 over 100 in it. Did that negative 3 over 100 have any bearing upon these zeros here? The answer is no, right? Determining what the zeros are and what their multiplicities are has nothing to do with any kind of number or coefficient you could put out front. The only thing this coefficient does is it multiplies y values essentially, right, by negative 3 over 100. So it affects how high things get or how low things get, but it doesn't affect where the zeros are or what their behavior is. So what I would suggest here is that we understand that if I stuck a constant out here, call it a for now, then that would not affect the zeros and it would not affect their multiplication. Now, in order to actually write the equation for this graph, we can't just keep an a in here, right? We need to know what number it is. But we can figure that out, and the reason we can figure that out is because I can see right here, right? I can see right there that 0, 4 is a point on this graph. So what that means is that if I plug 4 in for f of x, 0 in for x everywhere, oops, should be 0, then the only unknown is a, right? So now I can just solve this. So I have a times, well, 3 squared is 9, times negative 1. Negative 4 to the third power would be negative 64. So I get 4 is equal to a times 576 when I multiply that. And I can divide by 576. So we had 1 over 144 equals a. So now I know what my function is, right? F of x equals 1 1/44 x plus 3 squared times x minus 1 times x minus 4 cubed. So now let's just make that adjustment to our calculator and see if then we're looking the same as what's on this page. So I'm going to insert 1 over 144. And then that looks a whole lot better, right? And it's cutting through 0, 4 just like we want it to be. All right, so one more to try out here. All right, so I'm looking at the zeros. So it looks like we have x equals, what is that? Negative 5 with a multiplicity of 1. X equals 3 with a multiplicity of 1. And then here, x equals negative 1 with a multiplicity of 2. So we'll have f of x is equal to x plus 5 times x plus 1 squared, since it's multiplicity 2, and x minus 3 to the first. Okay, but again, we have a very specific graph here, right? That's going through very specific points. So just like in the last one, we should put a little a here out in front. And we can determine what that a is because we can see that we're going through the point 0, negative 2. And there's nothing special about the y-intercept. I mean, you could plug in a different point that you thought was really obvious. But if you notice that the y-intercept is nice, you might as well use it because it's always nice putting zeros in for x's. So here we go. Negative 2 is a times 0 plus 5, 0 plus 1 squared, and 0 minus 3. 5, 1, negative 3. So this is negative 2 equals a times negative 15. So it looks like our a is 2/15. So our function is f of x equals 2/15 x plus 5 times x plus 1 squared times x minus 3.